Since some of us are reminiscing on how we got to be in Tara Oceans, Lee and I were in Nice in February 2009 with many other people for the ocean. It's the Oslo, the ocean science meeting that was there. And we're going to lunch with Gabi, and Gabi started describing to us Tara. And on the spot, I said, we're going to put a sensor on for the whole time. And we went back to the U.S., and I called my program manager at NASA and said, we have to put sensor on the boat. Don't give me money for salary. Just give me money to be able to put the sensors for 1 year to show that it's worth it. And she bid. She was ready. She said, okay, we'll do that. We got $20,000 to start, and with that we managed to do the first year and then prove that the concept worked, we can get good data, and go from there. It was a great adventure, and thank you very much for Eric and for others that bought into that vision. So the first slide here is you see the group of different people from University of Maine who went on Tara Arctic. We all met the boat when it came back to Laval. Okay, I'll start from there. So here are the collaborators, both present and past. What I didn't say here is that we managed for Tara Arctic to get some funding also from ESA. They funded the pigments analysis, and they funded a sensor. So it's another space agency saw the value in this type of data set. These are people that were working on it. Okay, so why would NASA care about Tara or any space agency? The reason is that Tara was a true global expedition, as we heard before, where the exact same sampling technique was used in every place. And that's not the case in general in oceanography. In general, you have a boat going for 1 month, doing certain measurements. Even if there's community-wise agreed on protocol, they're not necessarily done exactly the same, because we all are married to the way we do things, not necessarily the way everybody else does it. And in Tara, there was an insistence on doing it one way, and that's the right way, and we all do the same. And so even if we're off, we're consistently off, so we can really talk about global patterns. And NASA specializes in global observation. So we did global exploration with Tara, but the global observation we can do from space, we cannot do any other way, as we do from satellite in terms of plankton world. So this is just as an example for scale. On a daily basis, we get estimates of phytoplankton biomass or pigment mass from space on similar scale as what Tara covered. And we have no other sources of in-water except for aggregating from many different boats. This was, again, a coherent data set. So a colleague from NASA, Jeremy Wardell, went and looked at, can we use the data we got from Tara, and how does it compare with other data that they used to validate algorithm with. So what we have here is chlorophyll is estimated from the spectrophotometer that we install on the boat versus MODIS satellite. And all the black dots are those from Tara. And all the gray dots are what they have in their alpha data set that they use to develop algorithm called the NOMO data set. And you can see that it's a significant number compared to what they have in there. And not only this, we have a lot of points in extreme oligotrophic ocean, which is very hard to get data set in because that's very far from shore. And Tara got there. Now, if we only use the pigment data from Tara, there's only few match up in the same time as the satellite. So it's not all the pigment we collected, it's all the pigment we collected under a condition where we could match them to satellite. So you have to have a perfectly clear day to do that. And then finally, you can see how well the spectrophotometer compared to chlorophyll based on HPLC. So here we have all the HP data set. And this is measured, this is data filtered by probably 20 different people. So we have all the different people that were on board contributing to it. The Tara data set also contained very high spatial scales because we continuously pumped water as the boat went along. It's called a flow-through or an inline system, and passed it through the spectrophotometer. NASA scale is about 1 kilometer square per pixel. Sometimes we get satellites that have several hundred meters. And one question we always have is when we take water and compare it to satellite, should it match? How well would they match? Is there a big variability within a pixel that might cause it not to match, even if we do perfect measurements? So we could use that. And again, in the same paper with Jeremy, what we did is looked at what's the coefficient of variance, the standard deviation divided by the mean for scattering within a pixel. So we took every pixel and looked at the coefficient of variance within it. And then we did the same for chlorophyll. And you can see that for chlorophyll, again, based on spectrophotometry, it's higher than for scattering. So there's more variability within a pixel. And if we look at the 99% level, you can expect one out of every 100 matchup to be as far off as 40%, even if you do perfect. You have a perfect algorithm from space and you have a perfect measurement with your HPLC. And then less so for scattering. And again, what we did not do, and that's future work, is look at it in a perspective of where we are in the ocean. This is aggregating all the data we collected, but we can divide it into coastal versus global, et cetera. We'd expect less variance as we go away from shore. Another thing that people do with remote sensing data is they develop local algorithm for their waters. And I was contacted about a year ago by somebody who worked on the Red Sea, and he told me, the only data I can find is Tara for the Red Sea. There's nothing out there. There's some fluorometry done by people in KAUST in Saudi Arabia, but really the only absorption and scattering measurement ever done in the Red Sea and throughout it were done by Tara. And he used it there's a paper that just came out a month ago where he's looking at, where he developed a local algorithm, and you can see here all the intricacies that one could see even in an oligotrophic place, relatively speaking, as the Red Sea. So people are mining our data set. We put them out there and they're mining. Sometimes we're part of the paper, sometimes we're not, but it's a wonderful, wonderful resource. Tara provides us things in very fine details. We heard 5 talks on with very high information content about the plankton world. When you observe from space, you get very little information. You get information on a pigment, maybe something on size, but not much. But as space agencies put more and more satellite and different satellite in space, the amount of information that we're going to get will increase. And for that amount of information, we need in situ information to develop algorithm. It's critical. So this is just an example. There's now, only in the last few years, people have started to develop algorithm for size. What we have here is pico, nano, and microplankton distribution in the ocean, based again on standard ocean color algorithm. And here you see from Colombon's paper, I think it's micro and pico here that he has, and how much information he can say about each one of those groups. But there is some relationship between them in terms of one could then see and validate whether these algorithms on site that are highly not validated from space, can they be put together. The other thing is that we got high temporal resolution, not in the same place, but we measured on a daily with and sometimes and on station many times over 2 days different aspects of the ecosystem. From NASA and other space agencies, we usually get, in the good cases where things are clear, an image a day. But that's not the direction we're going. We're now starting to work with geostationary satellite that provide you information every 15 minutes during the day. And even at night, one can get information using active sensors like LiDARs. So again, there's new frontiers opening in space that could have the temporal resolution that might be relevant to ecosystem-type processes. Terra measured, we just heard, continuously with the CTD Rosette as function of depth, so at 1 meter resolution, and then stations were done in 3 different depths. With NASA, most in space agencies, we get information only near the surface. But that, again, that's a direction that's opening up. With LiDARs, we can go down to depth, and I'll show you in a second. And also, there's profiling platform in the ocean. There's about 3,600 Argo floats going up and down in the ocean, and more we equip them with optical and biogeochemical sensors that provide information about the biology. So by coupling them together with BioArgo, this is an example of such a float with a sensor here, an optical sensor, we can extend the NASA measurement to depth, but also with active sensors such as LiDAR. And this is a theoretical study looking at how we could measure from space with high resolution with a novel LiDAR called Opal that is going to start hopefully measuring from airplanes next year and further on from space later on as other satellites come up. So just as an example of future satellite we're going to have. So PACE is already on the books. This is going to be, it's going to go to space around 2022. It will have very high spectral resolution, every 5 nanometer in the visible. That makes for about 80 different wavelengths from which we can hopefully get information about different pigments in the water other than just chlorophyll A, which we can do today. And using data from Tara, we were able to show that we can extract at least 5 different groups of pigment with hyperspectral absorption data. And we're now working on the HyperPro data collected on Tara to show what we can do with that. And it's very promising. So to prepare algorithm for when PACE is going to be up in the air. LiDAR is hoped to be in ACE. ACE is not yet on the books, but it's being worked on. PACE means pre-atmosphere, cloud, and ecosystem satellite. This is PACE, and ACE was supposed to be is supposed to follow, and that's, again, aerosol, clouds, and ecosystem. So these are 2 satellites that are predicted, that are supposed to work also on the interaction between atmosphere and ocean, and we know that there's a relationship between them. We're also going to have a polarimeter, and polarimeters provide more information content about what's in the ocean. We think we can use them to do composition of particles, whether there's more organic, more inorganic, better algorithm to detect coccolithophores, as an example. We're funded by NASA to start next year a 5-year project where we're going to go 4 times to the North Atlantic, doing a lot of these kind of measurement. We'll have an aircraft that will have a LiDAR on, a polarimeter, and a hyperspectral remote sensing. And in the same time, we're going to do a lot of the same measurement that we learned from Tara. We purchased instruments specific to instrument that was on the Tara in order to be able to match those measurements and hopefully then extend to the Terra data set. So to conclude, the Terra expedition provided the first truly global data set for optical properties and pigments for calibration validation exercise. It provides a wealth of data to develop novel algorithm for. For example, can we use algorithm for exports such as the one that Lionel has devised, Lionel and the group from LOV, to connect it to the measurements from space. And finally, as I hope I convinced you, there's a lot going on in the remote sensing world that will provide us a wealth of new information, not as much as you're getting from the genomics, but more information that these type of data set will be needed to develop algorithm and to calibrate and validate with. And hopefully, Terra Ocean is not going to be the last global ocean mission that will be used for that. Anyways, thank you very much.